Conops, concept of operations, specifically for CCTV surveillance, sensor deployment, and design in 3D using SketchUp. Create winning proposals, precision test the designs, and maintain satisfied customers. Concepts of operation, conops. Well, what are conops? Systems are deployed to accomplish certain goals and objectives as defined by the customer. This is the mission. Conops are the way in which an asset or technology is deployed and used to yield a specific outcome in support of the mission. Analysis and review of asset performance characteristics versus conops goes to establish the framework of the design. Does the asset, in the way in which it is deployed, contribute to the accomplishment of the mission? This is the question we ask ourselves. Ultimately, we want to ensure that the mission goals are achieved. In the context of this presentation, CCTV surveillance sensor deployment, well, what is CCTV? Closed-circuit television cameras, thermal imagers, SWIR, NIR technology used to maintain surveillance of an area by outputting video images. I'm not going to speak to the transport methods such as IP or legacy coax to get the images out at this point. These are optical sensors, though, and they have various performance characteristics such as field of view, sensor pixel density, and illumination requirements. 3D modeling. Well, what is 3D modeling? Well, we're all familiar with that. 3D modeling has been effectively employed by architects, mechanical, and other design engineers for quite some time, and is the de facto standard tool employed during the design process. We've all seen the little presentations in Solid Model Works as a software, or 3D CAD to present different design images so that you can see what the part or thing might look like before it is actually built. Using simple tools such as SketchUp, we can create a virtual environment that accurately depicts the deployment location. And we can also create graphical representation of sensor characteristics such as fields of view. SketchUp, as I've mentioned, that we're going to be using, it's a program that was a graphical program that was written by or developed by Google some time ago, and about a year and a half ago, so it was purchased by Trimble. It's online on the web. It's free for download. As a first example of conops, we're going to look at the surveillance of an airport, the customs green channel. That's the area in the airport where you go when you have nothing to declare. What do we want to put in there from our for analytics? Well, maybe facial recognition and watch list alert, item left behind, direction of travel violation, because people should be flowing in one direction and not the other. Maybe passenger count. These are all things that we'll find out from our conops analysis of what the customer wants. Other considerations we may have might be just passenger throughput, as far as we don't want to impede the amount of passengers. There's a minimum amount the passengers need to go through this area, and maybe we want to exclude the customs officers from any analysis or any recording. But let's take a look and let's focus just on facial recognition. Just take one piece. Facial recognition does require some specific sensor deployment requirements. First, minimal pixels, as defined by one of the leading vendors of facial recognition software, is that you need 32 pixels on target interocular, that's between the eyes, which is an average about 6.5 centimeters. All this works out to a value of approximately 500 pixels per meter is what's required as a value for the resolution of the imager. So an example, at 10 meters from the target, the lens we selected produces a horizontal field of view, the width, of about 8 meters. Okay. The sensor, or the imager, if it has a 4:3 format in the camera, would need to be, well, 8 meters times 500 pixels per meter would be 4,000 pixels in the horizontal, which would put us in the class of a 12 megapixel camera. Pose, which is the deviation from straight-on frontal, this equates to the angle of view from where the camera is viewing the subject, and equivalently the mounting height, therefore, of the subject cannot exceed plus or minus 15 degrees, or the person cannot be rotated plus or minus, should not be rotated more than plus or minus 15 degrees from straight on. The site model we're going to look at, basically we decided after we looked at it, and we'll see it in a moment here, it's going to be a 20-meter standoff from the entrance of the hall, and the basic entry channel will be about 5 meters wide. Okay, and now here we have the view of the entry channel. It's not any one specific customs green channel. It's just sort of representative of all the different ones I've been through in my travels internationally. You always see the sign, customs nothing to declare, and there's a green sign, so it's called the green channel. This is all created in SketchUp. You see I can select the wall over here, move it out of the way. It's just a component that I made in SketchUp. Very easy to make. Now, like for the example of doors, those are just components that were available in SketchUp. There's actually available for download. You can modify them a little bit and then just drop them back in place. Stanchions, again, just a component that's available in SketchUp. You type in the word stanchion, and other people have made models of stanchions, and even the people, the bags, all the items that you see here, for the most part, were already pre-made by other people out there, just other people working in SketchUp doing various modeling type functions. Mention the people, and those were all authored by other folks, and I just downloaded the models. But one thing I did add in here is I did put some scaling to them, so I can show that, for example, the little boy over there is about 1.3 meters, the young lady there is 1.69 meters, and the young man there is about 1.93 meters. That represents the range of, typically when you say I want to see have different subjects at different heights to be seen by a system, that typically represents the low range to the high range. The 1.93, which is about 6'3" US, that's up to the 95th percentile as far as height is concerned. Okay, but it gives you the range there, and that's one thing you can do, is validate if you're going to achieve the heights that you need to achieve in a specific model. Okay, now let's take a look at the basic dimensions we spoke of, and I'll use the measuring tape function here in SketchUp, and you see where the mount would be for the camera to the entrance to the channel. It's about 19.94 meters. I said about 20 meters from where the sensor will be to that entrance, and then use the measuring tape again to go from that stanchion pole to the other stanchion pole. It's about 4.4 meters, and I rounded it up to 5 meters just for our discussion's sake here. We're going to talk about camera lens selection, and what I've decided on is a 1/3 format imager, a 4:3 format, and there's so many different calculators out there available, but what you find if you plug the numbers in, that to get a 4.8 wide, remember I need that with horizontal field of view, 3.6 high vertical field of view, about 18 millimeters focal length, so you use a 15 to 50 varifocal megapixel lens at 20 meters, and there are specific megapixel lenses, but that's a different discussion. Given the requirement for 500 pixels per meter that we had before, plug all those numbers in the calculations, you find out that a camera in the range of at least 5 megapixels would be required. Down below I have a little diagram of it. Here we have the image that I created in SketchUp of a 3D model of that 18 millimeter lens at 20 meter standoff. See, 4.8 meters and 3.6 meters high, and then I added in a little box at the other end there, and I'll zoom in on that here in a second. There we go, and using that as to simulate the camera, and also gives me a little handle to use when I'm placing the image and trying to rotate it or change the azimuth, etc. Right, I Control-C, just like you do in any other application, to copy that image, and I'm going to now paste it, Control-V, right into the image I have here, into the virtual layout, and zoom in a little bit. Makes it easier to move the pieces around. And zoom in, I'm going to attach the camera box, so to speak, to the mount. I have to play with it a little bit sometimes. It's a little tricky trying to get it all lined up the way I want to get it centered on the simulated mount there as best I can. And of course, when you're doing a little demonstration, it never quite goes exactly as you'd like it to. But now we do have it in place, and now I'm going to zoom back out, and we're going to take a look at it, and we can see that, okay, this is the straight 0-degree tilt on the camera, with the camera up at approximately 8 feet, looking straight out. And what we see there is that there is a significant gap between the lower edge of the field of view and the floor, which of course is not the way the image should be placed, right? We would actually tilt the camera down, and we will do that in a moment here. But just to speak about this for a second, you can see, looking at the image there, that would be a representation of sort of what you would see on the monitor. A better representation, I'm going to pan around now and then sort of zoom in, and you can see the lower edge of the field of view there. That would be the bottom edge of the display that you would see, and you would see that the subjects there, the people, only occupy about the lower 1/3 of the image, which is kind of wasteful on an image, right? So that's something that we don't want. Now we're going to actually adjust the image, change the tilt on it. So I go ahead and select it and hit my hotkey there to do a tilt, and hit my hotkey, and I attach it, and I come out, grab a line there, and you can see I just checking to make sure I can tilt the camera the way I want it, and zoom back out, and then I'm going to come over here and look and be able to see exactly how I want to place it. Enable the tilting function again, and as you can see, I can move the field of view in the azimuth, positive and negative. If you look down the corner there, it says angle. The angle value is changing. That's the tilt angle. What I'd like to go for is approximately 5 degrees. So I can either run it till it says 5, or I could just enter the value 5, and it'll automatically snap to that number. Why 5? Because then that gives me remember I needed plus or minus 15 degrees pose, so this is like a preload of like 5 degrees tilt. Each of the squares on the grid is 0.5 meters, so we can see that the young man there, the tallest gentleman, he's got 2 squares about a meter above him. The other gentleman is about 1.5 meters above him. The young lady is several meters above her, and the young gentleman there, the young boy, has about 5 meters. He's only about halfway up through the field of view. So we can see that everybody's within the field of view as they should be. But more importantly, as we pan around to the side, we can get some more intelligence out of this. We can see that the field of view intersects the plane of the ground at about 5 meters out. So we have definitely 5 meters worth of distance for the people to traverse before they exit the field of view. But if we look again, the young gentleman there, and we see where he might exit the field of view, and just tracing it on out, right out there about the fifth, sixth, about the fifth tile out is where he would probably, his face would leave the field of view, because we're interested in the face and the facial recognition. And if I can go ahead and get a measurement on that in a second here, there's my tape and measure it on out, and it is about 8 meters. This is important because, let's say in our facial recognition system, perhaps we need a minimum amount of time that the person needs to be within the field of view for the system to process them. Well, with 8 meters, that would give them approximately 4 seconds being within the field of view. By hitting the perspective key, I can also look at this and analyze it from above, and see that here's my field of view against the grid of the floor. Again, measuring out, going out there at about those 5 squares, 5 tiles out, and seeing what the field of view width is. I can see it's about 3 meters at that point. The field of view tapers down as you know, it's a lens that tapers down as you get closer to the source. But looking again at that same 5 square out, 7 point something meters, 9.4 meters out, a little bit farther. I can see distances. I can measure different things virtually. Well, what's this distance? What's that distance? If I decide that I want to see, well, maybe one lens is not enough, maybe I want to stagger the lenses, I can just copy, paste in place, and grab the lens and move it over and decide on the appropriate amount of overlap that I want to have, and see what the conops, see what the performance might look like with 2 cameras covering the entrance there with some layer of overlap. between them. Obviously, that's the value that you'd have to work out, but one could very well see that how the system might hand off one subject to the one camera, one subject to the other camera. But again, this is something that could be modeled and very easily seen using SketchUp. In our next example, I'll use the example of surveilling an outdoor mall parking. And with SketchUp, I'll show the integration with Google Earth, exporting SketchUp shapes as georeferenced KMZ files, and in the same token, we can also import the KMZ waypoints as well. Here we have our blank SketchUp workspace, and up here we have a blue white eye and a blue field icon, which brings up the model info area, and one of the selections there is for geolocation. If I click on geolocation and add location, what that does is it shows the integration between SketchUp and Google Maps. Earlier, I'm from Florida, Orlando, Florida, so I typed in Florida Mall. Up there in the address field line, I just typed in Florida Mall, and it zeroed in on the Florida Mall there for me and gave me a nice representation of the Florida Mall from Google Maps. I then select the region that I want to import into SketchUp and drag that on out to extend it, and just hit click on grab, and it automatically imports that selection into my location. Again, go in there. I only got half the mall that time, so now when I get the other half of the mall, just reposition the image, select region again, and open them up, and then click on grab, and boom, it'll import and automatically seam it to the other selection. You can see this says USA, Orlando, Florida, and it gave me the longitude and latitude. And as I zoom in here, you can see there's no seams. It automatically aligns everything the way it's supposed to be. So let's position everything here the way we want it to be, and let's maybe focus in on just this one area here, this one building. And then look over here at this other shape that I designed. Here's a pole, 6-meter pole, with 2 PTZ enclosures at the top. Control C, copy it, and then just Control V, paste it, just as we've done before, directly into the workspace. And you can see the pole there, deciding where I want to put it. And let's actually, maybe the best place to put it is over here in this grassy area. Well, it looks like a grassy area, you know, that's at the end of the parking strip there. Position it in place there. And now I want to align the azimuth of the arm, so I'm going to zoom in a little bit here and grab it in a second there and align the arms so that they're facing north and south, or I could make it east and west, whichever you prefer, but I can do that very easily there. Okay. Next I'm going to do is, and I can see that I'm placed where I want it to be. Then next what I'm going to do is come up here and show another lens I've created, another lens shape I've created over here, and that's just a standard 1/4 inch CCD lens for a PTZ camera, set to about 8 millimeters, and looking out to about 75 meters, right? And if I do, it'll have the field of view as shown, about 33 meters in the horizontal and about 45 meters in the vertical. 45 in the horizontal and 33 meters in the vertical. Control C, copy, and then paste him directly into the workspace. There we go. I need to zoom out a little bit here and reposition the component so that I have the camera box that I created nearest to the pole, so I can grab him and drag it down to attach it to the pole. So I zoom in again and do some fine positioning. May have to zoom in a little bit more, but the SketchUp's pretty intelligent and automatically snap things if you have them in the right perspective. Hit my hotkey here, and I'll bring up my rotation tool, and now attach it to the lens field of view, and make sure I can rotate. Now I'm going to zoom on out, and so I can see exactly where I want to position the lens. reposition everything here, and then I can hit my key and rotate and put the lens looking at the parking area there right down the front of the building if I want. If that might be one way to do it there. Control V, because it's still in the clipboard, and position that lens there, rotate them around, grab the camera box and zoom in and do the same thing as I did before and attach it to the PTZ enclosure at the top there. You have to zoom in a little bit. Sometimes they say you have to zoom in a little bit. Sometimes it gets a little tricky, so you have to get them positioned just right. And if you don't zoom in to the right level, like I said, it'll automatically grab. But of course, when you're doing a demo, you don't always get it right. Okay, I think I've got it this time. Grab him on there. He's attached, and then attach to the lens. Make sure I can rotate, and then zoom on out again. And then I can go ahead and position my lens however I decide is the proper way. So they want it looking out here into this area of the parking lot. Well, it's PTZ, and have it looking wherever I want. Or maybe I want it as a default looking down the side of the building there. But in any event, what we have when we're all done is a 3D representation of the two fields of view of the lenses and the camera pole, the PTZ pole itself. Now, to show the integration with Google Earth here, there is a button up at the top here, and after I get it positioned here, there's a button up here. It looks like a little ball, little green. Click on that. It says show in Google Earth, or preview in Google Earth what this looks like. Those other lenses over there are ones I was working on earlier, but it automatically exports those shapes into Google Earth as KMZ files. So this is a Google Earth display. Google Earth is free, and KMZ's is the markup language for Google Earth to show waypoints and different things. It directly exports those shapes there, and you can see the fields of view, you can see the camera pole, and of course in Google Earth you have a lot more resolution to see the parking lot images. 3D model benefits. Okay. So what do we see? After capturing the conops, we created a site model to use in the selection and definition of the required sensors. It helped us out a lot. We were able to place the models of the sensors within the virtual environment to test the conops and the achievement of the mission goals. Were we seeing the people the way we needed to see, the proper fields of view? Were people being seen, throughout a sufficient area of travel? Mentioned about 8 meters, and if you're walking at 2 meters per second, that would give you about 4 seconds to the field of view. We're able to measure those things. We could rapidly test new conops to achieve requirements or suggest improvements. As you saw, I could just drop in another lens and we could overlap them to see if that's something that we might want to do to make things work more efficiently. We can try to develop and test potential product improvements. As we're working with the sensors in the virtual environment, we might be able to identify shortfalls in sensor performance and say, if the sensor worked this way or that way, if there's some improvement here or there, we can capture that information, test it, and then pass all that information on to engineering to try and get products developed that just improve the product line, improve the performance overall, and of course customer satisfaction at that point. We've seen that it's a powerful tool to present proposals to customers and quickly gain acceptance. So that with the KMZ export and just in general, it's a visual aid to let people know what's happening. Lastly, again, you can use this to create graphics of use case scenarios for sales and marketing because this presents the value proposition in a graphical form to the customer. If this presentation has been helpful, or if I can be of further service, please email me at mstrong591@gmail.com, or please reach out to me on LinkedIn.